Hello everyone, this is the review session for continuous motion chapter 12. This is the first part. So let's start. So the objective for today's session is we will talk about what is the difference between kinematics and kinetics. When we discuss or we attempt to solve a dynamics problem, the first chapter, chapter 12, is kinematics, but the rest of the chapters, 13, 14, and 15, is kinetics. When you solve a dynamics problem, you need to know whether this problem belongs to kinematics or kinetics. And that's how it will guide you whether this belongs to chapter 12 or the other part. So we'll discuss what is the difference between kinematics and kinetics. Then we're gonna list out the kinematic equations and discuss the characteristics of these equations. And finally, we're gonna talk about the problem solving of continuous motion, and we will discuss briefly discuss on 3 problems. So, kinematics of a particle. This is the first chapter you will have in your dynamics, and the first section is rectilinear kinematics. So, what is kinematics and what is rectilinear kinematics? So, rectilinear kinematics, by rectilinear, it means moving in a straight line path. So a particle is moving along a straight line path. If a particle is moving along a curve, then you can take derivative, and within that small step, it is still rectilinear. So, and by the word kinematics is the study of the geometric aspect of a particle motion. So, by geometric aspect, we mean that velocity, acceleration, position, and time. So these 4, I call it VAST, vast. These 4 are the geometric aspect, geometric detail of a particle in motion. When we limit our study only to geometric details or aspect, this is kinematics. So in kinematics, your dynamics problem will not have anything that is caused by force. So what we would do if your dynamics problem has force in it? That's the part kinetics, which is the study of the force that causes the motion. So this is how you can differentiate between kinematics, or a dynamics problem belongs to kinematics or kinetics, whether your problem has force involved. If it is, then it's kinetics. If there is no force involved, only VAST, that's kinematics. So let's now talk about continuous motion. Continuous motion is a motion that can be, in simple words, that if the motion can be expressed in using a continuous equation, that is continuous motion. So what are the kinematic equations for analysis using kinematics? There is 2 scenarios. One is variable acceleration, and another is constant acceleration. So for the variable acceleration, you have to use derivative forms that we know. Velocity is the change in distance, ds, over change in time. Also, we have the acceleration, which is change in velocity over time. And if you solve for dt from the first equation and plug it to the acceleration equation, or vice versa. If you solve for dt from the acceleration equation and plug it to the velocity equation, you will get the another form, which is ads equals to vdv, which is also an important kinematic equation when your acceleration is variable. You can also apply these equations for constant acceleration, but for constant acceleration we have simplified equations that we have derived. Again, for the variable acceleration, these are the derivative form. If needed, you can also use this as an integral form. Okay, so what we will do if we know that our acceleration during motion is constant, meaning a fixed number, 5, 10, 20, that's constant, not a function of time or position. So if your acceleration is constant, then these are the equations that's derived in your textbook. V equals to u plus at, final velocity v equals to initial velocity plus constant acceleration multiplied by time. Similarly, we have the position equation, change in position, s minus s naught equals to ut plus half at square, and we also have v square equals to u square plus twice as. So the limitation of the constant, these equations, which is simpler, but the limitation is these are constant, applicable only for constant acceleration, and these are for variable acceleration. So as I said, the acceleration could be a function of time. So for example, t squared plus 5 or t cubed plus t squared plus 3 something. Then it is easier if we use this formula, because it has a dt, and if your function is a function of time, then you can take integration a dt, then you can find dv. If your acceleration is a function of position, for example, s your position, s is square or twice s something, then it's better if you use ads equals to vdv, because if your a is equals to, for example, s squared plus 2, then you can take integration with respect to ds. It is easier. If you plug a equals to s squared, and if you want to take integration with dt, it will be difficult. So this is the trick that you have to remember. So let's move forward. Now let's discuss a little bit more on our equations. So we have listed the variable acceleration equation, and which is in derivative form, calculus form, and for constant acceleration we have just formulas. So if we look closely on these equations, we see we have three equations for variable acceleration and constant acceleration, but these three equations covers four variables. Those are the geometric details: v, velocity; a, acceleration; position; and time. Now we have three equations, but each equation, if you look at, has three variables in it. For example, the first equation, if you look here, velocity v, s is position, t is time. So it has three variables in one equation. Let's look at this one. It has acceleration, it has velocity, and time. So this equation also includes three variables. So this tells us if we have a relationship between any two, for example, if you have a relationship v in terms of s, so if your v is equals to or if you have relationship between v with respect to time, so if your v is t squared over t something, then you can replace this one with the t function and integrate with respect to t, and you can get the s. So if you have a relationship between any two, you can get the third one. Also for constant acceleration, you will see you have velocity, acceleration, and time. You have position, velocity, time, and acceleration. And here you don't have time. So if you need to find something and you don't know the time but you know the displacement, you can use this equation. But if you have time given, then you may want to choose this one or that one. And often, once you find one, if you find this or acceleration, and you can use the third equation. So let's solve or discuss, we'll not solve, we'll just briefly discuss three examples from your dynamics textbook, and see how we apply the equations that we have seen into problem solving. So the first problem says that acceleration A is given as a function of time, which is 2t minus 1. So it is a function, not a constant acceleration. We have to find velocity and position s at when time is 6 seconds. Also given when time is 0, so at the beginning, the start point, the position was 1 meter and the initial velocity when t equals to 0, these are initial conditions, velocity was 2 meter per second. So this is initial velocity, and this is the initial position. We have to find the final velocity and position. So let's start our solution. I'll just give you the hints and the answers. You have to do it yourself. So in this problem, we see the acceleration is in variable, not constant, and a relationship between acceleration and time is given. So let's look at our equations for variable acceleration, and we see a relationship between acceleration a and t. So which equation has a and dt or t? This equation. You have acceleration and time. So let's select that equation. Now we need to find velocity. So what do? We just take the dt on the other side, and now you have integral form. And if you plug a value, which is 2t minus 1, and take integration with respect to t, you will get this form, and that is your velocity. So if you plug t equals to 6 seconds, you will get your velocity 32 meter per second. So what you have to do, you have to follow the steps that I told you and match your answer. If you get something else, you can comment and I can help you. The next part is that, well, you have to find the displacement, the position. Well, which equation have position? Again, the concept was if you know relationship between any two, so now you have relationship between velocity and time. Which equation we need position? So which equation has this? We have velocity, we have time, we need position. So we select this equation and take the dt on the other side, and it is integral form. Now v is a time function, so if you put v here and take integration, this will be s, and if you take the time function integration, you will get this. We need the position at t equals to 6 seconds, plug t as 6, and you will get the position 67 meter. So do it yourself and check your answer, match your answer with this. So let's talk about another problem. So the previous problem, we had the acceleration as function. Now this problem, we have acceleration is constant. So the problem says you have acceleration, actually it's decelerating, negative, 2 feet per second square. And then it has a response time. So the problem is saying that the driver saw some people at a d distance ahead, and he was traveling at 44 feet per second. If the driver was not drunk, he needs 0.75 seconds to respond and press the brake, and the brake will decelerate at negative 2 feet per second square. But if the driver was drunk, then the response time would be 3 seconds. We have to find the minimum distance so that the car will not hit those person. So how can we do that? So let's work on our solution. Let's analyze the problem. It is kinematics problem, because it did not ask for any force, we need to find acceleration. The acceleration is constant, so we have to look for the set of equation, kinematic equation for constant acceleration. So once we have this, now we need to find distance. So which equation has distance, right? So we'll work on first case, assuming the driver was not drunk. It takes a response time of 7.75 seconds. So what happens during that time is that during that 0.75 seconds, the driver was still driving, and he needs that time to move forward. To press the brake, and within that time, the car is still going. So we have to consider that distance, even this was applied before the brake, right? So we can use S equals to Vt. Where do we get this equation? From this equation. If your acceleration is 0, since this was the response time before your deceleration, you are left with Vt. So you have to plug V equals to 44, and T is 0.75, which is the case 1, not drunk driver. And then you have to use this equation, because we don't know the time to brake, so we're going to use this equation. And the D is the distance between the car and then those people, and your initial S naught will be the response, the distance covered during the response time. So if you solve for D, you can find D is 570 feet. Case 2 for the drunk driver, right? What would be your V naught? V would be 0, because you're pressing brake, you want to stop, so your final velocity would be 0. Your initial velocity would be 44, and then acceleration is -2, and then you'll get this answer. So do it yourself and check your answer. Same case for case 2, we have to do when the response time was 3 seconds for a drunk driver. Again, we have to do S naught and find your S naught, and again plot on the same equation. This time S naught will be different because T is 3 seconds in this one, and you have to find the D. So you can find the minimum distance. Well, of course, if your response time is more, the minimum distance is more. So if the driver was not drunk, you need minimum distance to avoid an accident, which is 517 feet. If you are drunk, if the driver was drunk, and if his response time is 3 minutes, then the minimum distance would be 616 feet. Okay. So do it yourself and check your answer. The final problem that we want to talk about, since we have solved two problems, one was variable acceleration, one was constant acceleration in horizontal. This one we're going to do constant acceleration but in vertical displacement. So the problem says a ball was thrown from a 30-meter height building. So it was thrown above, it will go up high, and after some time it will drop down. And another ball B was thrown from the ground upward. The initial velocity of the ball A was 5 meters per second. The initial velocity of ball B was 20 meters per second. We have to find the height h from the ground where this ball meet or pass. So again, it's a constant acceleration. Acceleration was not given. So what is the acceleration? The gravitational acceleration, right? 9.81 meters per second. It is downward. So how do we solve this problem? So acceleration is constant, so we can use our 3 formula that we have learned for constant acceleration. So we can use either of these 3, right? So let's work on each of the particles. So let's choose particle A, or ball A. So for ball A, we need displacement or position. What is the height? So which equation has that? So we're going to start with this one. This one has that position. So here we start this one. We replace A with Z, and Z was downward. So that's why we put negative. S naught would be 30, and SA you are looking for that. and z is 9.81, right? So that's ball A. What about ball B? So this will be SB, actually, not SA, SB. S naught is 0 because it starts from ground, and initial velocity are given here. So here it would be 5, here it would be 20. So now you'll find SB. So if you find SA and SB, how can we solve for H, right? The problem says they are passing at that height. So when they're passing, their height H would be same. Their position is the same. So we're gonna use that concept, same position at passing. That means your SA and SB, SB from here, SA from here would be the same. If you equalize this equation with this equation, you will get you can solve for t time, because both of the ball was thrown upward at the same time. So the time during the travel was same. When A was going up and coming down and B was going up, the time of travel was same. So we have to find the time, t equals to 2 seconds. Now you can plug this t back to either this equation or that equation. You will get the height, which is same because they are passing at the same point, which is 20.4 meter. So again, do all these steps. I just give you the hints, and in class we'll solve other problems using the concept. Try to understand, apply the reason why we're selecting which equation and how the equations came. Read your textbook and we should be good. So that was it for continuous motion. In next class we're gonna discuss erratic motion. Till then, thank you.